Hi everyone, so now let's look at some tutorial questions for the surface integral of vector field. So this is the questions. So if sigma is the surface of a sphere, so this is the equation of sphere, you have to find the flux of the vector field. Okay, so this is a vector. Assume the flux is oriented outwards. So in order to find the flux, okay, of the vector field that is coming out from the sphere, okay, so we have to apply these equations. Okay, we have double integral, then we have the force, okay, the vector field dot product with the unit vector n, okay, which represent the direction of the flux, and then ds. Okay, so this is the formula. So the question have gave us the vector field. So now we have to find the unit vector n. So let's see what is the unit vector n. So the unit vector n, if according to the question, it mentioned that it is oriented outward. So if it is outward, okay, so we have to apply these equations. Okay, unit vector n equals to negative fx, comma, negative fy, comma, 1, okay, and divide with fx squared plus fy squared plus 1. Okay, so this is the formula. So first of all, okay, you have to ask yourself, okay, what is f, okay, before we're able to perform the differentiation with respect to x and y. So f is the surface, okay, that your flux will be coming up from. Okay, so here obviously the your flux will be coming out from the spheres, right? So you have to take the functions of the sphere. Okay, so for the sphere, the function is x squared plus y squared plus z squared equals to 4. So if you are going to use the xy projections later on when you are defining the dA, so here your f must be z, so your z will be 4 minus x squared minus y squared and then square it. Okay, so this one is your f, or this one is your z. Okay, so now let's find the fx. So fx is equals to 1 over 2. So 4 minus x squared minus y squared. Okay, so you will have 1 minus 1 over 2. And then you differentiate with respect to x, you get negative 2x. Okay, so when you simplify, you will get this 4 minus x squared minus y squared square root, and then you have divide here. Okay, and you have a negative, yes. Okay, so this is fx. So whereas for the fy, it will be quite similar to the fx. So we're just replacing it directly. Okay, so this one is your fy. Okay, so now we got the unit vector n, so we can combine the f and also the n. So we can combine the f dot product with the n. Okay, so for our f, we have a 0, 0. Yeah, we have just this, right? We have just the k component. Okay, that is z. Okay, so we dot product with the fx squared. Okay, so we have negative fx. Okay, we have negative fx, so become positive. So you have x over square root 4 minus x squared minus y squared. Okay, and then comma negative fy. So negative fy will give you y over 4 minus x squared minus y squared. Okay, and then comma you have 1. Okay, we have 1. So the ds I have cancelled out, so behind I will have the dA. No, this one no need first. We just perform a dot product first. Dot product first. Okay, here I will write ds lah. Okay, here I will write ds. So here will become dA. Okay, so I already cancel out the term at the bottom here. Okay, so this part already cancel out. Okay, with the term of the ds, so left the dA here. Okay, so the answer is equals to, yeah, you only has one z here, z dA. Why? Because these two things, they are 0. So when they multiply it, you will get 0. Right, z dA. Okay, now you can put it in our double integral. So we have a z dA. So we need to choose the projection that we want for the surface. So it is a sphere. Okay, so I think everybody, you know how does the spheres looks like. Okay, so this is a sphere, right? Okay, the sphere. Okay, so our axis z, our axis y, and our axis x. Okay, so if we choose the xy projections, okay, meaning that we'll be seeing this circle. Okay, this circle. Okay, so this circle, if you draw in 2D, this is a circle. If you draw it in 2D, the radius will be equivalent to, yeah, you can see these equations. Okay, if the z is 0, the radius will be 2. Okay, so the radius here will be 2. Since this is circular structure, so the dA, you can replace it with r, dr, and d theta. Okay, and the z, you can take the functions of the sphere, which is 4 minus x squared minus y squared. Okay, and then the integral for the r will be from 0 to 2, and angle will be from 0 to 2 pi. Okay, so let's transform to the polar coordinate. So this one is going to be r squared. So 4 minus r squared, and then square root. Then we have r, dr, and d theta. Okay, so let's press calculator. So the answer is 2.67 d theta multiplied with 2 pi. So we have a 16.76. Okay, 16.76. Okay, so this one represents the flux coming out from half of the sphere. That means this is the flux coming out from the upper hemisphere. Okay, flux from upper hemisphere. So if you need to find the flux coming out from the whole sphere, so we have to multiply 2. Okay, total flux from sphere. Okay, then it will be equals to 16.76 multiplied with 2. So equals to 33.51. Okay, so this will be the flux coming out from the sphere. Now let's look at the second questions. Okay, so now we have a surface of the cube. Okay, so this cube will be bounded by all these planes. X equals to 0, x equals to 1, y equals to 0, y equals to 1, z equals to 0, and z equals to 1. We have to find the outward flux, okay, of the vector field. Okay, so again, what is the equation to find the flux of the surface? Okay, so the equation that we have to use will be this one. Right, this is our equations. Okay, so again, F has been given, the N is not given, but we know that it is outward flux. Okay, so we can find it. But first of all, I want you to imagine this cube. So this cube doesn't have a single equations, like in the previous one, we have a single equation of sphere, right? But this one, the cube doesn't have a single equations. Okay, we know that it is a combination of all the planes. So let me draw this cube. Let me draw this cube. So if you draw this cube, so this is the cube that I have drawn based on the information given, because it says that the cube is bounded by plane x equals to 0. So this is the x-axis. So this is the x-axis. X equals to 0 refer to this point, and x equals to 1 refer to this point. Okay, x. Okay, so when we have this interval for the x, and we have interval for the y, and we have interval for the z as well. Okay, so you will see all these planes actually will form a cube. So I'm constructing the side of the cube using different colors. Okay, because I want you to see that this cube actually has 6 surfaces. Okay, 6 surfaces. Okay, so meaning that in order to find the total flux coming out from this cube, we have to perform these operations, okay, 6 times. 6 times. Okay, because we have 6 surfaces, so each surface has its own equations, so we have to do it one by one. Okay, now let's look at the flux coming out from the green surface. Okay, you can see the green surface, right? So the green surface will be the first one. I will use the green color to represent that, the flux that is coming out from the green surface. So the information we have on this green surface, that it is located, okay, located at the positions where the x is equals to 1, right? X equals to 1. Okay, so for the y and z values, it depends. Okay, it depends on the size. Okay, you can see that the y, okay, the y is ranging from 0 to 1, right? The interval, and the z also ranging from 0 to 1, 0 to 1. So this form the plane. Okay, so we refer back to the equations for the flux. So this is the equations. Okay, first of all, what is our f? So the questions have gave us the f. Okay, so our f is equals to, okay, we can still use the same f. So this is 2x, 3y, z squared. Okay, z squared. Okay, so this is the f. So now let's find the n, the unit vector n. So this unit vector n, okay, since the flux is outward, so we will be using the outward functions. So the outward function is negative fx, negative fy, 1, and then we have fx squared plus fy squared plus 1. Okay, so this is the value. So now we need to figure out what is our f. Okay, our f. So look at this green plane. The green plane is located at the positions x equals to 1. So we define the functions, okay, of this plane to be x equals to 1. Okay, so here we need to modify our unit vector n equations, because now our functions is not z. Okay, we are having this one is because our function is z. Okay, now our function is x. Okay, so we have to modify it. So how to modify it? So here, because it is x, right? So this part will be going to, let me replace, okay, with 1, okay, positive 1. And then this part is going to be minus f z. So means that you have to differentiate it with respect to the z. Okay, so when we differentiate with respect to the z, so the fy is 0. Okay, so the fz is also equals to 0. So at the end, the whole thing will become very easy. Just 1, 0, 0, and fx. Okay, so this one is telling us that if see, this one is 0, this one is 0. So only the I direction has the flux. Okay, so this is telling us that our this thing will be equals to I directions. Our flux will be in I directions. So you just imagine, maybe it's very hard for you to imagine how does the flux coming out from the solid. Why not you imagine like this? You just imagine this cube is filled up with water, and then you make the surface to have many holes, so the water will burst out from the hole. Okay, so when the water bursts out from the hole, it is like the flux of the water coming out. Okay, coming out from the surface. Okay, you can imagine. So all the flux, when it coming out from the surface, will be in this direction, right? In the x direction. So x direction is the positive I directions. And that's why over here, you have your unit vector n in the I directions. Okay, in the I directions. Okay, right, so this one is the unit vector n for the first surface, and we can now combine it with the f. Okay, so since you don't have the I component and j components, okay, so this will become 2x. Okay, 2x because you cross product, 2x and then dA. Okay, so dA. So this dA will stands for the interval, right? The interval of the surface, of the green surface. Okay, I already explained to you, for the green surface, we have our interval y, 0 to 1, interval z also 0 to 1. So you can replace it with 0 to 1, 0 to 1, okay? And then 2x, and then dy dz. Okay, so the x over here you could replace with 1 because this is a surface, x equals to 1. Okay, so you can replace it with 1, so it becomes 2. Okay, so we can do the integrations. So the answer is equals to 2. Okay, so this one will be the flux coming out from the green surface, 2. Okay, the green surface. Now we go to the second surface, okay, which is the orange color surface. Okay, this one, the orange color surface. So imagine the water coming out from this surface will be in the y directions, right? Okay, or will be in the j direction. Later we will see this. Let's find out the flux. Okay, so we'll be using the same equations. Okay, so the first thing that we have to do is find this n. Okay, so find this n. So I will use the general first. Later I will show you how I modify it. Okay, and then to get this positive y directions flux. Okay. Alright, so now we need to find out what is our f, what is our surface equations. So this orange color plane is located at the position y equals to 1. Y equals to 1, and the x is ranging from 0 to 1, and the z is also ranging from 0 to 1. Am I right? Okay, so meaning that our f now is equals to y, and it is equals to 1. So which one I should modify it? Okay, so I should modify this part, okay, and make it to be 1. And then this part is going to be negative fz. Okay, so fx equals to fz will be both 0. Both 0. So turn out to be this one you have 0, 1, 0. Am I right? Okay. Okay. So you see this, you know that, okay, your unique vector n, later on, okay, when you put it in, it will be in the j directions. J direction. So you can combine now with the f. So since it has only j, okay, we look at our f. What is our f? What's our f? Let me see, what is our f? Our f is 2x, 3y, z square, dot product with 0, 1, 0. Okay, the a. Okay, so meaning that now I have only left this 3y. So this 3y, the a. So the a will be the interval. So here we'll be using the interval 0 to 1 and 0 to 1. Or it's the same thing. Okay, so we will have a dx, dz. So in this case here, the y, you have to replace it with 1 because it is at the positions 1, right? Okay, so the answer is equals to 3. Okay, equals to 3. You can try yourself. Okay, so this one is for the second surface. Okay, imagine you have to do it all the surface. We have done the green, the orange. Now we go to the red. Okay, we go to the red. This one maybe we have to do it quickly because we already know the concept for the red surface. So for the red surface, you're using the same equations. This is the equation to find the flux. But in fact, if you don't, because you already understand this concept, right? You understand the concept of defining this flux. But this one is easy because the surface is flat, consistent. For example, y equals to 1. It's consistent. There is no other variable, okay, that determine this surface. So it will become very easy. So for the red one, you will know that the unit vector n will be pointing downward, which is the negative k directions. Okay, so you can just use this one, negative k. Okay, so we'll do it quickly. So for this one, the n is equals to negative k directions. Okay, so the f, okay, we will just consider the z, okay, and the a. Where this thing from? Okay, because I skipped the step, so I will explain one more time. Then in the following, I will just skip the step. So it's 2x, 3y, z squared. Okay, dot product with unit vector n. So as I told you just now, this will be 0. This also will be 0. This will be negative 1. Because it's negative k. So when we dot product, this one gone, just left this z squared. So you put the z squared above. Okay, so now you define the interval for this one. So this one would be dx dy, right? So dx dy both from 0 to 1, 0 to 1. So all the plane, they are same size. Okay, so you can press calculator. So this z square, so what is z? The function of the plane. Okay, the function of the plane. So this one is located at the positions, the z is equals to 0, right? Yeah, the z is equals to 0. Okay, so meaning that the whole thing is 0, then the answer is also 0. Okay, so this one is for the red plane. For the red plane. Okay, we go to the next one. Go to the next two. So we have completed these 3. Okay, the blue one. Okay, the blue one. Okay, so for the blue one, let's see the blue plane. Okay, so this is the equations again. So any idea about the direction of the blue one, the flux coming out? The flux, the water, if you pop many holes, the air will be definitely in the negative y directions, okay, or negative j directions. Okay, so I will write negative j. So the F dot this will be equals to, so you will just refer to the j component. You need a dot product with the j component, so it will be negative 3y. Okay, so you put this thing negative 3y, okay, and dA. Okay, so you need to replace the y value. So you look at the blue plane. What is the y value? For the blue plane, the y value is equals to 0, right? And the x, they're all in the range 0 to 1, and the z also. Okay, since this one is 0, okay, so you don't need to do it. This one is 0, so the answer is 0 for the blue plane. So similar also for the last one, the purple plane. So the purple planes, the flux is in that directions. Okay, that is the negative I directions. Negative I directions. Okay. Purple. Okay, so the purple plane. So the F dot N will be equals to, because it's X, just the I part, so it will be negative 2x after you perform the dot product. So for this one, okay, okay, your X is located at the position 0. Am I right? The plane. Okay, so for the Y is 0 to 1. Z also 0 to 1. Okay, so again, you don't need to do anything because this one will give you 0 because the X is 0. So the answer is also 0. Okay, so how many surfaces we have there? See, so many, okay? And the last one is the blue one at the top. Okay, blue one at the top. Do you think the blue one at the top would be 0? Okay, so this is the blue plane. So now let's see how the flux coming out from the blue one. So of course the flux will be going out. Okay, so it is in the positive k directions. Positive k directions. Okay, so now we dot product the F with this. Okay, so since we dot product with the k, so you will have this z square left. Z square. Z square. So you integrate z square dA. Okay, so for the blue plane, it is located at the position z equals to 1. So the x, okay, and the y, they are all in between 0 to 1. Okay, so here you can replace 0 to 1, 0 to 1, and the z you replace with 1 square. So this one will be dx, dy, so it will be 1. Okay, so find the total flux. Okay, total flux, finally. Okay, so the total flux will be equals to, you add all of them together. Okay, So you can start from here. 3, 0, 0, 0, 1. So it's 3 plus 1 equals to 4. Okay? Oh yeah, I still got 2 here. 2. So it will be equals to 6. So this is the total flux then coming out from the cube. You see, this one you have to do it 6 times. 6 times. Okay, so later on I will show you in maybe our next lecture how to actually simplify this process by using the divergence theorem. So you no need to do it surface by surface. Just single one equation, you'll be able to know what is the flux coming out from the solid. Okay.